Hi, welcome in the first lectures in this series of 7 lectures on high-dimensional statistics and probability. So today we'll talk about the curse of dimensionality. But before starting the course, I will give you some more information on the organization of this course. So how is this course organized? First, I remind you that this course is quite a conceptual course on mathematical course. The main objective are to understand the main features of high-dimensional observation, to learn the main concepts and method in order to handle the curse of dimensionality, and very importantly, to get prepared for a PhD in statistics or theoretical machine learning. So there are 2 parts in this course, 7 weeks with me, and then either 7 weeks with Mathieu Loral or 3 weeks with Tristan Marihuard. I will come back on this later. Just right now, actually. So in the 7 weeks with me, so we will cover these 7 topics. And then with Mathieu, you have 7 weeks on the central probabilistic tool for machine learning and statistics. And if we are with Tristan Marihuard, then you will have 3 weeks on algorithmic aspect, illustration, and the supervised classification. So how is the course organized? So first, you will have some recorded lectures, so exactly as this one. And this lecture will be displayed on the YouTube channel, which is given here, that you can find on the website of the course. So the website on this course is at this address. You also have some lecture notes, so the lecture notes will be available on the website of the course. And in addition to the lecture notes, you will also have some handwritten notes, which will correspond to the handwritten notes that I will display during the lecture. You have some exercises that you will have to search. So you look at the lecture and you work out the lecture notes, and then you do the exercise. So you have a list of assigned exercises to each week, and you have to work them out in order to do some progress and to understand the topic. And once you have done all this, so we will have some interactive sessions. So it will be every Tuesday at 10 p.m. And what I will do, I will first start with a short recap. Then we take some time for question and for discussion on the topic. So you cannot come all together to this interactive session. So half of you will come in person, and the other one will follow on the big blue button channel, which is this one. And again, I will send you the link by email. And at the end of this course, so in December 15, so you will have an exam on this part of the course. And this exam will be with 2 parts. A first part, which will be on 7 points, which will be on a part of 1 or 2 of the exercises of the assigned list. And then you will have 13 points, which will be on a research problem. So how to work out this course? So the idea is really to learn by doing. Okay, so what you have to do first is to look actively at the recorded lecture. Okay, so you do not have just to look, I don't know, in your sofa before going to sleep. You really have to look actively. So what does it mean? So first you have to try to understand all the explanations. If at some point something is not clear, then what shall you do? Press the pause button. Okay, the pause button is really your friend. So you press the pause button, you try to understand, and once you have understood, then you release the pause button. And if you do not understand, then look at the lecture notes in order to understand, and then proceed with the following of the lecture. Also, at some point in the lecture, I will ask some questions in order to have kind of an interaction. So in this case, what you have to do is to press the pause button, try to answer, and once you have found an answer, release the pause button. Okay. It's quite hard to stay concentrated during several hours, so there will be some break, and I will show you some coffee break, something like this. So when you will have the coffee break like this, I think it will be a good time to have a short break before going to a new topic. So then, once you have looked actively at the recorded lecture, you will work out the lecture notes. So what shall you do? You should take a pen, take a sheet of paper, and then redo all the computation. It's very important to learn by doing, not just by listening to me, but by doing it by yourself. And the idea is that you have understood something when you are able to do two things. The first thing is to explain this to someone else. And the second thing is to be able to answer the following question is, why have we done this computation, or when have we done these things instead of something else? Okay, so this is really important, and this is a good test to know whether you have understood something or not. Okay, so once you have worked out the lecture notes, you will have some practice, and for the practice, what you will do is to work out the assigned exercises. So you have 2 exercises every week, so you will be busy. And once you have done all this, you come and participate to the interactive sessions, so either in person with a Big Blue Button channel. So what are the documents for this course? So there are the lecture notes, so you have the PDF file that you can find on the website, and I will also give you printed version. You will have the handwritten notes that you can download on the website. So you have the website of the course where you have all the information, including the link to the YouTube channel of this course. And also there is a wiki website for sharing solutions to the exercises. So you can share your solution to the exercises. So there are already some people that have written some solutions. They might be okay, they might be wrong. It's really something for you, for sharing the solution. It is not a solution that is certified to be correct. Okay, so about the evaluation. So for the first part of the course, as I told you, you have an exam in December 15. And for the second part of the course, so with Tristan, there is no exam. And with Mathieu Loral, we will have a second exam, which will be late in January. And okay, Mathieu will give you some more information about this. Okay, so do you have any questions so far? If yes, so the best is to ask me next time that you see me to have more information about the point that you have not understood. All right. So we can start now talking about high-dimensional data and case of dimensionality. So today's data are very high-dimensional. If you think about, for example, biotech data, when you censor thousands of gene expression level or proteins expression level, proteins level in the blood of people, you really get a lot of information. So you have some data which where you observe many different quantities on a single person. If you think about an image or a video as you are looking at, so you have millions of pixels or of voxels if you have 3D images. Marketing or business data also censors many different quantities. Crowdsourcing data also can be very rich. So if you think about today's data, most of these data are really high dimensional. So this really thing sounds like a blessing. Why does it sound like a blessing? Because if you sense many variables on each individual, it means that, okay, you should be able to have all the interesting information and to scan every variable that may influence the phenomena that you are studying. So in a sense, it is a good news because you have plenty of information on the people and you will not miss something. Unfortunately, there is an issue with this, which is called the curse of dimensionality, which is that in general, and I insist on the in general, it is almost impossible to separate the signal from the noise in high-dimensional data. And also, you may have some big issue in doing some computation with this high-dimensional data. So let me explain this to you now. But before explaining this, it seems that I need to have a coffee. So see you later. So now I'm ready to explain to you the curse of dimensionality. So we spend something like 20 minutes where I will explain to you different aspects of the curse of dimensionality. So all these aspects are related, but I think it's important to have them in mind, and then we will move to a more mathematical part. I will describe 5 curves of dimensionality. There are some others, and I will mention at least 2 of them, but they are the most important one. So the first one is very simple. It is the fact that fluctuations cumulate. So let's take a very, very basic example where you have n observation of a random vector x, which has a covariance matrix, which is, let's say, sigma squared times identity. And what you want to do is just to estimate the mean of x. So if you want to estimate the mean of x, what do you want to do? Well, you want to use the sample mean. So we'll take here the sample mean, and let's try to understand how far is the sample mean from the mean that you try to estimate. So we can look on average at the average square distance between the sample mean and the quantity which is the true mean that you want to estimate. And this is a very basic computation, so you can take the norm, which is the Euclidean norm here. So this is the sum of the square of each coordinates, okay? And of course you can switch the expectation of the sum. And if you look at this expectation here, what you recognize is simply the variance of the GS coordinate of the sample mean. All right? So now you can come back to your very first course on probability and statistics, and you should know that the variance of the sample mean will be exactly 1 over n, the variance of one of the components. So it will be sigma square over n. And since you have p coordinates, this is p times sigma square over n. So now if you look at this formula, so what you observe that, so when you are in dimension 1, you have sigma square over n, but here you have p times sigma square over n. So this distance here, so this is the average distance, but if you look at the average distance, you see that it goes, so to the square, it goes linearly with p, which means that if p is much larger than n, which is something which is quite classical in actual data, this quantity can be very large and even huge if p is much, much larger than n. Right? So even the sample mean is not a good estimator for something that simple in high dimension. So that's probably the most simple curve that we can explain. Let's move to another one, which is about the loss of locality in high dimensional space. So let's take again a very basic setting where you have a value of interest, which is y high, that you want to explain with some variable xi, which is a variable in dimension p. Okay, and we will assume that each coordinates of xi, so xi is of dimension p, which means that you are sensing p different quantities, so for example p-gene, okay, and you want to explain so yi with this p quantity, and we'll assume that this quantity are between 0 and 1. So nothing fancy, nothing going to infinity, it takes value between 0 and 1. So we assume that the quantity of interest, y high, can be explained as a function of the xi plus some noise. And if you think about conditional expectation, we'll come back on this later, this is exactly what we will have. And here we make an assumption, which is a classical assumption, which is that function here is a smooth function, okay? So this is a very nice setting. This is a setting that we are used to in a low dimension, where y is a smooth function of the entries plus some noise. All right. So here, just to have a more probabilistic model, so we assume again something which is not fancy at all. So I told you that each coordinate of the xi are between 0 and 1, and we assume that they are uniformly distributed between 0 and 1. So again, nothing fancy, and also that they are independent. So it means that if you look at the covariates xi that you want to use to explain yi, they will be uniformly distributed on the hypercube 0, 1 to the p, right? So u here is the uniform distribution. So in such a setting, usually what are you doing? Well, if you think about the estimators that you know, which can be, for example, the k-nearest neighbor, or it can be kernel smoothing, or any other estimator that you know, actually, what it will do is to take an average, or maybe with some weights of the xi which are close to x. Okay, so if you want to predict the value of y at a point x, so for some covariate x, what you will take is an average of the observation yi, okay, for all the xi which are close to x, and you can weight more or less the observation depending on the distance between xi and x. And yes, you have seen this kind of estimation in your course in statistics, and you can prove that this is the best that you can do in low dimension, and it works very well. Okay, so let's try to understand if it works in high dimension. So for this, what I will do is I will look, so here I have n observation of xi which are uniformly distributed on the hypercube. I will look at the distance between two observations. Okay, so here what I have done, I have sampled n points. Okay, so they are sampled uniformly on the hypercube, z1 to the p, and I take increasing dimension. So here I have dimension 2, here I have dimension 10, here I have dimension 100, and here 1000. So if we look first in dimension 2, you have the picture that we are used of. There are some points which are close ones to the others, and there are some points which are further. Okay, so you can find some points which are close, and you can do your local average in order to estimate. Okay, so this is a local average of the y high, and this is something that you can do. All right, so now let's increase the dimension. So when we increase the dimension, what you see is that you have some kind of wave which is traveling to the right, and which is becoming more and more peaky. Okay, so if you look at the extreme at dimension 1000, which is not a large dimension actually. If you think about dimension of several million, you can imagine that you will have like a Dirac mass. Okay, so if you look in dimension 1000, what you observe is that all points are far away one to the others. Okay, and there is no point which are close. They are almost all at the same distance. Okay, the distance between the pair which is here and the pair which is here is almost the same. So you do not have any meaning of locality anymore. You cannot use anymore this idea of local averaging. First, because locally you don't have nothing. So even if you increase the ball, what is the difference between points which are that close and points that are that close? It is almost the same distance. All right. So I understand that it may look quite weird. Can we understand this? It's a very simple computation, almost the same as the one that we have done before. So let us compute the mean square distance between 2 points which have been sampled uniformly on 0, 1 to the p on the independently. So again, we can take the square norm. So this is the sum of the square of the coordinates. All right. So each coordinate follow a uniform distribution. They are independent. So what we have here, we have p times the expectation between two uniform distribution to the square. This is a very simple computation. You can compute it and you will find that it is equal to p to the 6. So here what we see is that the square distance grows like p to the 6. So if you just take the distance, it will be like square root p. So you see that distance between points are becoming larger and larger, and this is what we observe on this picture. So now we try to explain why this is becoming more narrow. Okay, and for this we look at the square deviation of this square distance. So I will look at the standard deviation, of the square distance. So what is the standard deviation? This is the square root of the variance. So this is the square root here of the sum of the variance because we have independence, and each coordinates are independent because you have been sampled uniformly on the hypercube. So what you have the square root p because of the p here, and here you have the variance of the difference between two independent uniform random variables on 0, 1. You can compute this. It is something like 1.2 times square root p. So what you see is that the standard deviation grows like square root p. So it grows at a scale which is much smaller than the p here of the distance. All right, so the distance are increasing. The standard deviation also is increasing, but with a power which is 1/2 compared to 1, so in a much lower way. And this is why we observe something here which is more picky. All right, so this is a simple explanation of this plot. At this point, what you may tell to me is, okay, but you have a fixed number of points, which is 100, and then you have enlarged the dimension of your space. So, of course, if you have a fixed number of points and you enlarge your space is larger and larger. So we can expect to have the points here which are further and further because you do not have, you fix the number of points and you enlarge the dimension. So maybe one question that you can ask, and you should ask this question, is, if I do not want to have this picture and I want to have this picture, how many points do I need? If I enlarge the dimension, how shall I enlarge the sample size? And what you will see is actually you really have to enlarge the sample size in a huge manner. So why? This is actually related to this fact. So if you take a ball in dimension p, there is something which is striking. So this is a Euclidean ball, of course. Something which is striking is that the volume of a Euclidean ball is shrinking. Okay. So if you take a ball of radius r in a p-dimensional space, okay, so VPR. So first you know that it will scale like r to the p with a radius, right? Because we are in a Euclidean space. So it will be r to the p times the volume of the unit ball. Okay. And if you compute the volume of the unit ball, so you have an exercise on this. I'm sure that you have already done this exercise. You can compute this volume, and you can observe that it grows like this when p goes to infinity. So what you have here is something like a constant over p to the power p over 2, and you have 1 over square root p times p, okay, which is also shrinking, but let's forget about this term and focus on this term. So here what you see is you have something which is decreasing more than exponentially fast, actually. Here you have exponential minus p over 2 times log p. So you are decreasing very, very, very fast to 0, and this is what you can observe on this picture. Right. So now, even if here when you have r to the p, r is a constant, so you see that r to the p times this quantity will again shrink like this to 0. All right. So whatever the volume of your ball, the volume of your ball is shrinking very fast to 0 in high-dimensional space. So you can say, okay, but if I enlarge the radius, how much do I need to enlarge the radius in order to have a constant volume? Well, just have a look at this formula. So here I have r to the p, and here I have p to the p over 2. So it means that you need that r to the p compensate p to the p over 2. So you need to have a radius r which grows like square root p if you want to have a fixed volume in your ball, right? So you really have to need to have a ball which have a large increasing radius if you want to have a fixed volume. All right. So let's see what it means in terms of sample size. So the question, I'll remind you, is what is the sample size that I need if I want to have this kind of picture here instead of this kind of picture in dimension P. So how much do I need to enlarge n, which is the sample size? Okay, so we will not ask much. We'll simply ask one thing, which is, okay, what I want is that when I do my average, I want to have at least 1 point, okay? So what we are asked is that for any point x, I want to have at least one observation on average, okay? So I will ask to have on average at least one observation. So how many points do you need for this? It's time for you for the first question. So I have represented here in yellow. This is the hypercube. So this is here in dimension 2, of course. So what I want is for any point x, so let's say that I have an x here, what I want is to have at least one observation, which is a distance at most 1. So what does it mean? It means that x must be in the ball around one of the observation. So what you need is that each observation, if you look at the ball, then the ball around each observation should cover the hypercube, right? So what you should have is that the hypercube 1 to the p, it must be included in the union of all the ball of 1 around the observation xi. All right. So now, what I want to know is how many observations n do I need in order to cover my hypercube. So for this, what you can do, something very simple, is to compare the two volumes. Okay. So the volume of this if you want to have a coverage, the volume of this must be smaller than the volume of the union of the ball. And the volume of the union of the ball is always smaller than the sum of the volume. So you must have at least this. And this volume is exactly the quantity that I have shown to you, which is Vp1. So what you will need is to have that this volume, so what is the volume of a hypercube in dimension p? It is always 1. So what you need is to have 1 smaller than n times Vp1. So in other words, what you need is that n is larger than 1 over Vp1. All right? And I remind you that we have seen that Vp1 is shrinking very fast to 0, so we will have n which will grow very fast to 0. So if we take the formula that we have shown before, we observe that n must be larger than 1 over the volume, which grows like this when p goes to infinity. So here you have something exponential p over 2 log p, so it grows more than exponentially fast with p. All right? And this is really huge. If you take this quantity and you look for different dimensions, for dimension 20, you have something okay. 30, ooh, it starts to be quite huge. If you find any kind of biologist which is ready to have such a large experiment, just tell me. And then you see that even for 100, it is just something that you cannot imagine. And for p equal to 200, then you see that it's more than an astronomical number because it's larger than the expected number of particles in the universe. So what this means, what we have seen here, is that we cannot hope to have this picture in dimension more than, let's say, 10 or 20, okay? In 100, you are sure that this cannot work, all right? So you cannot expect to have something like this, and that's the reason why you have to do something, because if you want to have local averaging, you would need a sample size which is much too large. All right, so this is really due to the fact that high-dimensional spaces are huge. So if you want to fill a high-dimensional space, you need a huge number of points. Let's see now another curse of dimensionality. So maybe the best is that I explain this to you on the blackboard. So here I have drawn a Gaussian distribution, so something which looks like a Gaussian distribution. So in dimension 1. So here this is so the maximum of the density is at 0, and I call it GP over 0. And here what I have represented in red, I don't know if you see the red, is a GP0 divided by 1000, so something which is very small. Okay? And I draw a line at this level, and it cuts the density here. All right? And the question that I ask is, what is the volume, which is here in yellow, right? So what is the volume that we have here? So in dimension 1, of course, this volume is almost 1. Okay, all the volume is here. You do not have volume in the tail. The tail are very, very thin. So you do not have volume in the tail. Okay. So let's look what's going on in higher dimensions. So I remind you that if you look at the probability density function of a Gaussian random variable, so we take a standard Gaussian random variable, so you will have 1 over square root p square root pi to the p exponential minus the square norm divided by c. So you really have very thin tails. The probability density function is decreasing very, very fast when x is going to infinity. So let's see what's going on when we move in large dimension. So here, so I have this picture, but now I do the computation in dimension p. Okay, and what I plot here is how it decreases when p is going larger and larger. So what you can see is that for small dimension, most of the mass is in the bell, all right? So it is in this region, in yellow here. But when p increases, you see that the mass in this yellow region is going to 0. And it is going to 0 very, very fast. And when you are in dimension 30, you don't have any mass anymore here, okay? So in dimension 30, you do not have any mass anymore in the yellow region. So how can we understand this? Well, this is related to this fact. So if you look at the volume of a ball, all right, we have seen that it is r to the p times the volume of dimension 1. So now let's look at the volume in a crust. So what is a crust? I'll do a picture for you. So here I have represented my ball of radius L. So this is this ball here. And what I want to understand is what is the volume which is in this crust. So this is just next to the frontier of the ball. So here I take another ball which has a radius which is 99% of the radius. Okay, so this is really just, we are just looking very close to the border of the ball. And what we want to understand is what is the volume of the ball which is in this region here, which is in red, which corresponds to the crust of the ball. So let's have a look at this. So since the crust is the volume of the ball minus the volume of the smaller ball, you just have to compare this volume with this volume, right? And using this simple formula, what we obtain is that the volume in the crust is r to the p minus 0.99 to the p r to the p divided by the volume of the ball, which is r to the p. So at the end, you obtain that the fraction of the volume which is in the crust is given by this quantity. So of course, when p is small, like in dimension 1 and 2, as we are used to, the fraction which is here in the crust is very small. Okay, in dimension 2, we see that this is very small. But when p is going to infinity, you have 0.9 to the p, which goes to 0, and it goes to 0 exponentially fast. So it means that the volume, which is in the crust, is going to 1 exponentially fast. So in large dimension, all the volume of the ball is in the crust here. All right? So really, this is something which is important, which is that you have to forget about your low dimensional intuitions. Ball are small, all the volume is on the surface. So what is the connection with what we have seen before? Let me show you this. So now what we will do is to compute the mass which is in a crust of size epsilon. Okay, so I look at a crust like this, where I have a ball of radius r, and I look at a crust of size epsilon. So this is my standard Gaussian. Okay, so I look at the mass of a Gaussian distribution in this crust. So I will rescale by 1 over epsilon, just because as we take epsilon goes to 0, of course this returns to 0. So if I want to have something which is constant, I have to rescale by 1 over epsilon. And it seems that I have forgotten to do it here. Anyway, the result is correct then. So okay, so you should have 1 over epsilon here and there. So if you look at this, what you observe, so you can just write down the fact that you integrate on the crust the probability density function. And to compute this, what you will do is change of variable. So we do a polar change of variable. So if you do a polar change of variable, so here you will have the radius, so it is r squared, and the volume you will have p r to the p minus 1 dr. Okay, so this is a quantity when epsilon goes to 0, and if I divide it by 1 over epsilon, that you can recognize, and this is equal to this quantity. Okay, so if you look at this quantity here, so here you have something which depends only on p. Let's forget about p. Here I have something, so this is the dependence with r, and what you observe is that when r is small, so this is 0, this is 1, and when r is increasing, this is increasing while this is decreasing. But this is, at the very beginning, it is increasing very fast, while this is decreasing not that fast, and after some point, this is decreasing faster than this is increasing. So for which r is this volume the largest? Well, this is exactly for r equal to square root p minus 1. All right? So it means that if you look at your Gaussian distribution, okay, the mass, where is located the mass? It is located in a crust of a ball of radius square root p minus 1. All right? So really the picture that you should have for a Gaussian standard variable, this is not the first picture that I've shown to you, but this is really this picture where the mass is concentrated on a crust. Let me show you this. All right, so when you're in dimension 1 or 2, at least when you are in low dimension, this is how you can imagine that a Gaussian distribution is. So you have most of the mass around 0, and you have very thin tails. When you are in large dimension, this picture is completely wrong. The mass is not close to 0. You don't have mass here. All the mass is around an area which is at a distance square root p of 0 g. All right? So essentially, the Gaussian distribution in large dimension is not something which is concentrated around 0, as here, but this is almost a uniform distribution on the sphere of dimension square root p. So when you think about the Gaussian distribution in large dimension, really you should think about something which looks like a uniform distribution in the sphere. And this is really due to the fact that, of course, the PDF function looks like this in high dimension, but since the volume is increasing when you're going far away from 0, you have a balance between the two. So when you are close to 0, the volume of the space is small, but the PDF function is large, but the volume of the space is small, so you don't have that much mass. And then when you're going far away, so the volume of your space is increasing. Of course, the PDF is also decreasing. At some point, the two are at the same level, and this is where you have all the mass, and then, of course, the volume of the space will continue to increase, but the tail will decrease much more faster, so we don't have mass too far away from this. So most of the mass is really around this circle, because if you look at the mass which is in the crust, as we have seen, this is something like exponential minus r squared over 2. So this corresponds to the PDF function plus p times p minus 1, sorry, times the logarithm r, and this corresponds to the volume that you have in a crust in a p-dimensional space. And this is why all the mass is more or less in this crust. Right, so really you should think about your Gaussian distribution as a uniform distribution of the sphere. I'm not joking when saying this. So another curse that we can emphasize on is that the fact that Will signals will become lost when you have high-dimensional observation. So, for example, imagine that you have some measure of the expression level of a gene. So you will have n repetition for p gene. Okay, so the gene here will be indexed by j, which goes from 1 to p, and you have n observations which are indexed by I. Okay, so what you observe is zgi. So theta j is the expression level, and you have a noise for each observation. All right. So what you want to find is a gene for which theta j is non-zero. Okay, this will correspond to the fact that they are active, I don't know, in some disease or in some regulation or something. And again, we assume that we have a very smooth noise, which is Gaussian. All right. So if you want to find the genes for which theta j is non-zero, what you can do is to take the sum of all the observations and we scale them by 1 over square root n. So if you do by 1 over n, so you will have an estimator of theta j, but here we scale by 1 over square root n. Why? Because this will stabilize the variance, because since you have a Gaussian observation, you directly have that this quantity is a Gaussian distribution with mean which is n times theta j divided by 1 over square root n, so square root n theta j, and the variance which is 1 over n times n times sigma square, so you just have a sigma square, right? So if you look at this quantity, what you want to say is that if theta j is 0, then you will have a Gaussian distribution in dimension 1 here, because I'm looking at quantity in dimension 1. So this should be small. And when theta j is non-zero, well, the mean will be square root n theta j, so xj should be large. So you will be able to detect if a gene has a non-zero theta j just at looking how large xj is, and to know at which level you must threshold the value. Well, you can just remind yourself that if you look at the probability that the Gaussian random variable with variance sigma square to be larger than 2 sigma, you know that it is smaller than 5%. So typically, what you will be able is to detect genes which have an expression level which is larger than 2 sigma over square root n. So if n is large enough, you will be able to detect a gene which has an expression level which is even not that strong. All right. So this makes sense when you look at a single gene. But now, so this is very classical statistics. I will not spend too much time on this. But now you will look at p gene at the same time. So if you look at p gene at the same time, you need to understand how this behaves when there is no signal over the p gene. All right? So there is a very classical result, and we will see this, I don't know, in less than half an hour, which is that if you take p Gaussian random variable, with n0 sigma square distribution, then the maximum of this Gaussian random variable, it should be to the square here. I'm sorry, I forgot to put a square. It is equal to 2 sigma square log p. Okay? So the maximum of wj to the square is something like 2 sigma square log p. All right? So if you want to know if theta j is larger or not than is non-zero, then you need to have theta j which is larger than the noise. So you will need to have theta j which is larger than the square root of this quantity. Okay? So when you consider pg together, you will need a signal to be larger than this if you want to detect that it is non-zero and not just only detect the noise. If to take a level which is smaller than this, then you will detect some noise and you will say, okay, this gene is active, but it is not true. All right? So if you want the signal to dominate the noise, you need to have a signal which is strong enough. And as you can see, you still have sigma over square root n, but you have this square root log p here. And if p is very large, like millions of genes, then this can be not so small. Okay? So as you can see, when you look at many different genes at the same time, so when you have a single gene, you can have a good detection of genes which are non-zero. But when you look at all the genes at the same time, which in a sense is a good news, because if you look at all the genes, you will not miss an important gene. But if you look at all the genes, you will not be able to detect weak signal. You will only be able to detect signals which are larger than this quantity. So this is another curse of high dimensionality. So there are some other curves, for example, and this is really related to what we have seen before. One rare event is rare. Many rare events may not be so rare because the probability of each event is small, but when you sum all the probability, it can be large. And this is related to a failed discovery that we will see in the last lecture. And another point that I do not discuss now, but we will discuss later, which is the fact that you need to have a low complex algorithmic complexity if you want to be able to do computation, because if you have something like exponential p in terms of complexity, then you will not be able to do any computation if your algorithm scale like exponential p. Okay, so usually if you are in large dimension, you cannot hope to have something with a complexity which is larger than p to the square, and even p to the square is p 1 million. Okay, good luck if you are able to do something like this. All right, so it was a sketch of different courses of high-dimensional data. So it is important to keep them in mind, and now we will see what we can do and why there is a hope that we can do something. Because, okay, you may say, okay, we have seen that we need to have a number of observations which is larger than the number of particles in the universe, so maybe it is completely hopeless. But fortunately, we are not estimating data which is a random noise. What we estimate is data which comes from an image or from a biological system or from some social interaction or human technologies. And because of this, you will have some structures, right? All these things are kind of a big, let's say, dynamical systems, okay, which are their own structure. We can be social structures or geometric structure or whatever you want. And because of this, usually what you have is that, okay, your data is living in a high-dimensional space of dimension p, but they are concentrated around low-dimensional structure, okay? And since they are concentrated around low-dimensional structures, if you are able to identify these structures, then you will be able to do stats in low dimension, okay? And this is more or less the path in order to do something in high dimension space. So what you want to do is to do some dimension reduction. So you want to reduce the dimension of the space in order to be around these low-dimensional structures. And you can do it in different ways. One way that most of you should know is unsupervised dimensional reduction. So what you will do is just try to, you have a cloud of points in dimension p, like represented here. So here p is equal to 3, and you want to approximate this point by the projection on a space of lower dimension. This is what principal component is doing. And we may wish also to do something which is more supervised, as I will discuss in a minute. So first, I'll just remind you briefly what we are doing in principal component analysis. So you have your n observation in dimension p. So these are the black dots here. And what you want is to project them on a plane, so which is represented in red here. And what you want, so a plane or a space of dimension d. So let's say a plane here because we are in dimension 2. So you want to find the plane of dimension 2, so such that the distance between the point and the projection, so the cumulative distance between the point of the projection to the square, is as small as possible. So you want to have the compression which is as good as possible. Okay, and this is what is represented here. So this plane seems good in order to approximate the point. You see that all the points are close to this point, so it seems that they are all close to this point, and it is probably you can represent the point in dimension 2 instead of dimension 3. So if you are not that familiar with principal component analysis, you can have a short recap on PCA in this exercise, and I encourage you to look at it. So PCA is working well. This is an example. So these are scan digits. So we have 1,000 of scan digits. It's the famous MNIST dataset. So here I have an image. So it is a 16 by 16 image. So here you have an array, but you can encode this as a vector just by stacking all the rows one below the others. So you will have a vector in dimension 256. All right. And what we do is to project the image on a space which is learned by PCA, and this will be a space of dimension 10. Okay, so we project the images in dimension 10. So we project them on the 10 first principal axes of given by a principal component analysis. And what you see is when you do that projection, so of course you have some loss, but still you can recognize the letters. So it means that probably you will be able to work with these letters by working only in dimension 10 and not in dimension 266. Okay, so we have been able to compress the data, and this is simply due to the fact that, okay, the 8s are very different, as you can see. So this is a sample of 4 different 8s. They are very different, but still there are some geometric structures so that you can compress the data in dimension 10 without losing too much. So this is an example where it works well, but sometimes PCA is not exactly what you want to do. I'll show you another example to understand that. So here what you are looking, so you are looking at E. coli. So E. coli, what is it? It is bacteria that you have in your gut. I don't know exactly the name in English. Maybe it is not the right name. So this is the bacteria that you have in your body, let's say, and some of them also are the outside of the body. So yeah, there are some of them which are very nice. You need them in order to have your digestive system working, and they are represented in black here. And some of them are very bad, and they can even kill you. Usually they just give you tourista, but sometimes they can kill you. They can, give you some very bad infection on your skin. So here they are represented in green and red. So green is for the one that gives you tourista, and red for those that will give you some bad infection on the skin. Okay, so we have done some chemical measurement of on different strains of E. coli. So we have different strains of E. coli. We do chemical measurement. So here the dimension P is only 55, so it is not that large, and N is 162, so it is larger than P, so it is not that bad. And it wants to do a dimension reduction. So if I do PCA, what I observe is, so in dimension 2, what I observe is this cloud of points, okay? And okay, so this is a projection. And as you can see, it does not give you any information about the difference between nice E. coli, which are in black, and bad E. coli, which are in green or in red. Okay? So now we may wish to learn a plane where we will see the difference between the two. Okay? So here this is unsupervised. We just try to reduce the dimension by finding the best projection. Now we want to find the best projection in order to understand what is the difference between the two. Okay, so for example, if you do LDA, then you will find this plane. And as you can see, you have interesting information about the two. Now, if you look in this axis, you can look at the difference between nice E. coli, which are here, and bad E. coli, which are here. Right? So the interest of having some supervised dimension reduction is that you will do some dimension reduction, but which is related to your problem. And here my problem was to understand the difference between nice and bad E. coli. Okay, so this is really what we will do in the following, which is try to find some structures in the data that will help us for our estimation problem. Okay, so a short recap. So we have seen that we have high dimensional data and usually not that large sample size. So there is the curse of dimensionality, but because of the way data is generated, we have the existence of low dimensional structures in the data, and you want to find these hidden structures. So we don't know these structures, so that's the point, we don't know these structures. So you want to find them in order to exploit them and to be back in more low dimensional problems. All right, so this is really what we will do in this 7 lectures. Oh, now that we have seen the curse of dimensionality, I will give you a glimpse on the mathematics involved in high-dimensional statistics. So, if you take the classical statistics, what you have a small number of parameters, you have a large number of observations, and this is exactly what you have in this kind of picture. So you have n points with n large. You want to find the best line to approximate this point. So a line is with only 2 parameters. Okay, so if you want to understand the behavior of the estimation of this line, what you can do is to investigate the performance of the estimator when n is going to infinity. All right? And typically, what you will do this with something like a central limit theorem, something like this. So this is the classical setting in statistics. If you think about the actual data, you really have an inflation of the number p of parameters. And typically, what you will have is that in the base case, the number of parameters p is as large as the sample size, and quite often the number of parameters will be much larger than the sample size. Okay, so it means that we must change our point of view on statistics. The asymptotic that n is going to infinity cannot fit anymore to this setting. All right, so we have to take another point of view, and we can typically think about 2 possible settings. One possibility is to consider a case where still we take some asymptotic, but both n and p will go to infinity. Okay, so if n and p goes to infinity, you have to say how p is going to infinity with respect to n. Okay, so you will assume that p is going to infinity as some function g of n. So it can be exponential n, it can be n to the square, it can be square root n, depending on what you want to understand. So this is the double asymptotic setting, and there is another setting which is a non-asymptotic setting, where the idea is really to treat n and p as they are and not take any asymptotic. Okay, no limit. So both approaches are their nice features and the bad features. So if you consider the double asymptotic, what is nice is that it is much more easy to analyze, because when you take limits, it's much more easy than doing precise computation, which is correct and irrevocable. And also you can have a sharp result, in the sense that typically when p and n will go to infinity, this is just like when you take random walk, when you take, well, let's think about the central limit theorem. So if you take a sum, an average of quantities, so it has distribution, which is a convolution of n distribution, but when you take n which goes to infinity, then the central limit theorem tells you that essentially you have something which is Gaussian. Okay, so when you take asymptotic, usually you can have precise, sharp results. The point is that if you want to use this kind of result, which is very nice, it is very sensitive to the choice of the function g. Let me say that, for example, so this is typical quantities in biological data, for example, that you have sample size which is 33, and you have 1000 parameters. So the question is, in order to understand the performance of my estimator, shall I consider that g of n is n to the square, or that g of n is exponential n to the 5, divided by 5? So, okay, in both cases, okay, if you take 33 to the square, you will find something like this, and you take exponential 33 divided by 5, you will find p like this. So both of them fits. But if you look at the result, so when you take n goes to infinity, in this setting, in many cases, you will say, okay, I am able to do something. And in this setting, very often, you will not be able to do something. Okay. So as you can see, it's very hard to have a conclusion for your data when considering asymptotic results. So it gives nice, sharp results, but it's hard then to come back to your data. So the other point of view is to take the non-asymptotic point of view. So in this case, you do not have any ambiguity because your result will include both n and p, and you just have to plug the value. So you don't have to wonder what is the g here. But of course, there is a price to pay for this, which is that the mathematical analysis is much more involved. And also, usually you do not have results that are sharp, especially in the constant. Okay, but this is the point of view that we will have. So we always have a non-asymptotic point of view. So we only do a non-asymptotic analysis. And I will describe to you now what are the tools that are involved. So it is time to switch from the slide to some unwritten note. Before we switch to the handwritten lecture notes, I remind you that you can find them on the website of the course. So if you go here on the website of the course and you scroll down, you will find here, so for each lecture, handwritten lecture notes and slides. So if you go on the notes, you will find the lecture notes. And if you look at the slide, you will find the slide that I have shown to you before. So you can find all the material here each week. So you don't have to write what is written, just download the handwritten lecture notes. So let me give a glimpse of the mathematics of high-dimensional and non-asymptotic statistics. So what are the typical quantities that are involved when you're doing some machine learning or statistics? Typically, we look at some, let's say, empirical process. So you have n observation in dimension d, you have a function, so it's assumed to be high d, at least independent. You have a function f from rd to r, and you want to compare the empirical average with the expectation. All right? And sometimes you want to look at this quantity over a whole family, capital F, of function f. So when you are doing some asymptotic statistics and you want to look at this kind of quantities, what do you have? You have a very important result, which is the central limit theorem, which tells you that if you look at the difference between the empirical average and the true expectation, you multiply by square root of n, then this converges in distribution to a random variable z, which is the Gaussian random variable whose variance is the variance of f of x1. So let me give an example of use of this. So if f is a L Lipschitz function, from R to R. So we take variable in dimension 1, xn, xn, which are independent with variance which is sigma square. So if you look at the variance of f of x1, so you can write it at 1/2 of the expectation of f of x1 minus f of x2 to the square. If now you use that f is Lipschitz, so this is smaller than L squared times x1 minus x2 to the square, right? Here you recognize the variance of x, so you can always upper bound the variance of f of x1 by L squared sigma squared. So now if I use the central limit theorem here, I will have that when n goes to infinity, that the empirical mean, the probability that it is larger than the expectation plus L sigma over square root n x. So by the central limit theorem, you know that it will convert to the probability that z is larger than L sigma x, where z is the z here, and this quantity, so since you know that the variance is smaller than L square sigma square, you can use a classical bound for the tail of Gaussian random variables. For example, the lemma B4, which is in pages 292, and it tells you that this is smaller than exponential minus x squared to the 2. Okay, so this is really a typical result from asymptotic statistics. You use the central limit theorem in order to get this kind of control. So the question is, can we get non-asymptotic version of such statement? Right? So if you want to have statement which is true for any value of n, you need to have some non-asymptotic version of this. And we can have such a result by using concentration inequalities. So we'll focus on the Gaussian random variables. So I will give only result for Gaussian random variable. With Mathieu Loral, you will see a more general result. And also if you follow the nice course by Pascal Massard that you can also find on the YouTube, in another YouTube channel, you can find much more on concentration inequalities. So here we will focus on the Gaussian case. So we assume that we have xn, xn, which are IID with a Gaussian distribution. So they are of dimension 1. So it will be a n0 sigma square distribution. And we will consider a function, capital F, of xn, xn. Okay, so this is a function from Rn to R. And we will assume that it is L Lipschitz. All right. So in this case, we have this result, which is state, so it is theorem B7 in the lecture notes. There is a proof in the lecture notes that you can look at, but this is only for people who knows about stochastic calculus. We can give a simpler proof with not as good constant, but here this is a short proof based on stochastic calculus. So we'll not prove here in the lecture, but you can look at the proof and the lecture notes if you want. So what we can prove is that in this setting, there exists an exponential random variable, xi, which has so an exponential distribution with parameter 1, such that we have this inequality. Okay? So if you look at f of x1, xn, it will be smaller than the expectation of f of x1, xf plus L sigma square root 2 times xi. So what it means? It means that the upper deviation of f with respect to the expectation is upper bounded by L sigma times square root of 2 times an exponential random variables. Okay, so this is a very strong result, and an equivalent statement of this result is to say that the probability that f is larger than in expectation plus L sigma square root 2x, this is smaller than exponential minus x. All right, so these two statements are equivalent. All right, so can we have such results for a fixed n based on the concentration inequalities? The answer is yes. So for this, what we do, we look at the empirical average for a function which is L Lipschitz. So if you look at the empirical average, we take the difference between x and y. So first we use the fact that f is L Lipschitz. So here we can upper bound the difference by L times xi minus yi. And then you simply use Cauchy-Schwarz inequality in order to say that this is smaller than square root n times the norm of x minus y. So here you have that the difference between the two average, it is always smaller than L over square root n times the norm between x and y. Okay? So what we have seen is that the empirical average here, this is a n over square root n Lipschitz function. So we can apply this result, or in this form if you want, to this function f, which is the empirical average. So let's do this. So I take the empirical average, I subtract the mean, I look at the probability that it is larger than L sigma over square root n x, right? So here I had L sigma, but because it was the L of the Lipschitz constant for capital F, so here the Lipschitz constant for capital F is L over square root n, so this is why I have L over square root n here. So this probability is smaller than the probability that square root 2 sigma is larger than x, so it is exactly equal to exponential minus x2 over 2. So if I compare this bond with this bond, what I observe is that what I have obtained is actually a non-asymptotic statement for this bond, right? So as you can understand, non-asymptotic, to get non-asymptotic bond, you need to have concentration inequalities, and the Gaussian concentration inequalities is really a very powerful tool because it is very simple, and that's why one of the main reasons why the lectures will really focus on Gaussian random variables, because we have tight constant and very clean bound in this case. All right, so this will really be a central tool in high-dimensional statistics. So let me give another example where we use Gaussian concentration inequalities. So let's take now a random variable epsilon, which follows a Gaussian distribution with covariance the identity. So it is the n-dimensional random variable with covariance equal to the identity. So now I want to say something about the norm of this quantity. So if I look at f of epsilon, which is the norm of epsilon, well, by definition, it is well Lipschitz. So I can apply again this concentration inequality. So x1, xn will be epsilon 1, epsilon n, which are the coordinates of epsilon. Okay. And what I have is that f of epsilon, so the norm of epsilon, is larger than its expectation, plus the square root of 2x, sorry, it is smaller than exponential minus x. Okay, this is really this upper bound. So this is what Gaussian concentration inequality gives you. And now I want to say something about this expectation. So this expectation, it is not very simple to compute it, but we can have an upper bound, which actually is a sharp upper bound, as we'll see in a minute. So if you look at this expectation, you can use a Jensen inequality in order to upper bound it by square root of the expectation of the square of the norm. And the expectation of the square of the norm, so it is just the sum of the expectation of the epsilon I square. Okay, so this is equal to 1. So this is equal to square root n. So you have a simple upper bound on the expectation of the norm of epsilon, which is square root n. And if you plug this upper bound here, you have that the probability that the norm to be larger than square root n plus square root of 2x, sorry, this is smaller than exponential minus x. And you can take the square of this and obtain that the probability that the square norm of epsilon to be larger than n plus 2 square root of 2nx plus 2x, this is smaller than exponential minus x. So Gaussian concentration inequality directly gives you this, but there are some other way to get it also. So this is an exercise, and it is one of the two assigned exercise for this week. which is to recover this bound from Markov inequality, and actually from Chernoff method. So this is something that you should practice. So I will let you look at this for next week. So there is something that I must emphasize. So when your function f, if you take your function f, so f is one Lipschitz. If you look at minus f, so minus f is also a Lipschitz. So you also have this inequality here, which is minus f is smaller than exponential of minus f plus L sigma square root 2 psi. Maybe I will write it on the blackboard, it will be better. So if I look at minus f, so minus f is also L Lipschitz. So if I look at exponential minus f of x1 n, yeah, it is a minus here, it is smaller than x minus, so the expectation of minus f of x1 n plus, so the remaining term, which is sigma square root of 2 psi, so this is a domination. And now, if I multiply this, I move this on this side and this on this side, what I obtain is that f of x1 xn is larger than the expectation f okay, and I move it on the other side, so minus sigma square root of 2 psi. Right, so Gaussian concentration inequality, so I give you with a domination of f by the expectation plus some deviation, but you also have a lower bound, so f is larger than the expectation minus some deviation. So we can use also this bound, and this is what we do now. So now we'll exactly do what we have seen on the blackboard. So we will use f of epsilon, which is minus the norm of epsilon, and the Gaussian concentration inequality, so give us this inequality. So we want before, here we have used the fact that this is smaller than square root 10, but now we do not have a lower bound for this. We cannot use Cauchy-Schwarz on the other side, okay? So let's try to have a lower bound on this quantity. And what is nice is that we can get lower bounds by using Gaussian concentration inequality. So what we have seen before is that the norm is smaller than the expectation plus this deviation. So if I take the square of this inequality and then the expectation, what I obtain is that the expectation of the square is smaller than the expectation of the square. This we have already computed. It is equal to n. And here, for this quantity, what you can use is Jensen inequality. So what we have is that x gives a plus square root 2x to the square. This is something which is concave, so this is very easy to check. You can do it, just expand the square. So since it is concave, you know that the expectation of this function is smaller than this function of the expectation, okay? And the expectation of exponential random variable with parameter 1, it is equal to 1. So you obtain that n is smaller than the square of this expectation plus square root 2. All right? So what we have proved is that this expectation is larger than square root n minus square root 2. Right? And what we have seen before is that when using Cauchy-Schwarz here, we have seen that it was smaller than square root n. So with Gaussian concentration inequalities, we have been able to localize this norm. And as you can see, okay, this is not very different from square root n, at least when n is large. This expectation is close to square root n. Right, so at the end, you can plug this lower bound here, square root n minus square root 2, in this bound to get a deviation of the norm from below. All right, so this was for bounding, having a non-asymptotic bound on empirical processes. So now I want to look at cases where we have supremum. As I told you at the very beginning, sometimes we want to look at supremum over some class of empirical processes. Okay, so for this, so if we are able to have some deviation, it's great, but we have deviation compared to expectation, so we need to say something about the expectations. This is what we will do now. So let us look at bounding expectation of supremum, and we will start with deviations, which is the most simple case. So let's start with a very simple case where we have independent random variables, and we look at the maximum of independent random variables. So I know you have already seen this, so this is just a short reminder. So if you look at the probability that the maximum to be larger than t, it is 1 minus the probability that all the variables are smaller than t. Since they are independent, this probability is the product of the probability. And now you can write that the probability that xj is smaller than t, that 1 minus the probability that xj is larger than t. Okay? And so here you have equalities. And now if you think about the case where t goes to infinity, so when t goes to infinity, all these probabilities are small. And since they are small, you know that the product here, so if you expand this product, you will have 1. Okay? And then you will have the sum of these probabilities, and then you will have a product of probabilities, so it will be smaller. It will have a smaller order. So this quantity, so you have 1 minus 1 minus the sum, plus quantities which are smaller. So this is equivalent to the sum of the probabilities. Okay, so you all know this, this is just a short reminder on this. So when you have independent random variables, you know that the probability that the maximum to be larger than t, when t is large, this behaves like the sum of the probabilities. And actually, you also know that whatever the random variable that you have, the probability of the maximum is always smaller than the sum of the probability. This is just the union bound. So in a sense, what we have seen before is just that the union bound is sharp when we have independent random variables. Alright, so this is for deviation, and now we want to look at expectation of maximum. So we'd like to use this same kind of union bound. So first, what we know is that if we have a positive random variable, since the maximum of positive value is always smaller than the sum of positive value, you have the same kind of bound, which is that the expectation of the maximum is smaller than the sum of the expectation. Alright, so this is for positive random variable, and usually it is not very sharp. For example, imagine that the mean of xj is 3, then for all xj, then you will sum p times 3, which maybe is much larger than the expectation of the maximum. Okay? So we want to have something which is more tight. So the first inequality that you can use is the following one. So if you take any value alpha, what you have is that the maximum of xj is always smaller than alpha plus the maximum of xj minus alpha. So this is the inequality. If you take the positive part, now it will be an inequality. Okay, so if I do not take the positive part, it is an equality. And if I take the positive part, it becomes an inequality. So I want to use this, so I plug this inequality in my expectation, and what I obtain is this inequality. So this inequality looks quite basic, but in many cases, it is enough in order to get a bound on the quantities that we are looking at. So let me give an example for this. So I will consider some random variables which are Sub-gaussian. So what does it mean? It means that they have expectation 0, and if we look for any s, any scalar s, we have that the expectation of S of xj, this is smaller than the exponential of sigma square S square over t. So this is what we call a sub-Gaussian random variables. And of course, if you consider a Gaussian random variables with a variance sigma square, you can check that you have this expectation, and here you have equality. So when you have a sub-Gaussian random variable, so if you have already seen some sub-Gaussian random variables, you know this, but I do a recap for those which have never seen this. So what you can do if you want to bound the tail of sub-Gaussian random variables, you can use Markov inequality. So this is lemma B1 in the lecture notes. So if you take the Markov inequality with the function exponential s of x, then what you obtain is that it is smaller than exponential minus st times exponential minus s of hj. All right? Now, you can plug this bound here, so you obtain this bound, okay? And this is true for any parameter s. So now what you want to do is to optimize in s, so this is what we call the Chernoff method. So you will do an optimization in s, so you just take the derivative and you find that the s for which this quantity is minimal is s equal to t over sigma square. So for this value of s, you plug it in, you obtain that this is smaller than exponential minus t square over 2 sigma square. Okay? So simply with the Markov inequality and with the optimization in s, we get a bound on the tails of sub-Gaussian random variables. And what you see is that you have tails like Gaussian random variables. So this is a good reason to consider sub-Gaussian random variables. But now what I want to do is to use this inequality in order to get a bound on the maximum of xg squared. So I will use this inequality, but not with xj, but xg squared. So of course, I can, if xg squared is also random variable, so if I plug a square here and a square here, this bound is still true. So let's do this. So I plug this bound here for xg squared, and I compute this quantity. So if I look at this random variable, okay, so this is a positive part of xg squared minus alpha, so it is non-negative. And since it is non-negative, you know that the expectation of a non-negative random variable, this is simply the integral of the tail function. Okay, so the expectation is the integral of the probability that xg squared minus alpha is larger than t. Okay, so I have removed the positive part because t is positive, so it will always be the same with or without the positive part. Now I can use this in order to, so I can use an upper bound on this quantity. So here we have seen that the probability that xg is larger than t is upper bounded by this. So if I look at the probability that xg squared is larger than t, so this is the probability that xj is larger than square root t plus the probability that minus xj is larger than square root t. So I will use this bound. So I will have a 2 coming from the fact that I'm looking at plus and minus. And so I look at xg squared larger than alpha plus t. So I will have square root of alpha plus t to the square, so just alpha plus t, divided by 2 sigma squared dt. All right? I think you should do this computation by yourself. So at the end, what I obtain, so this quantity, so I will have exponential minus alpha over 2 sigma squared. Okay, I have a 2, and I integrate exponential minus alpha over 2 sigma squared dt, which is equal to 2 sigma squared. So here I will have a 4 sigma squared. All right? So I have obtained this bound. So this bound is true for any value of alpha. Okay, so I have alpha plus this quantity. So now I want to get the best possible bound. So again, I will try to find the alpha for which this bound is the smallest, and for which value of alpha it is the smallest. It is for alpha equal to 2 sigma squared log of 2p. Okay, so if I plug this value of alpha, what I obtain is that the expectation of the maximum of xj to the square this is smaller than 2 sigma squared log of 2 exponential p. 2 EP, sorry, pas exponential p, c'est 2 times e times p. All right, so with this simple bound here, we have been able to prove this bound on the expectation of the maximum of the square of Sub-gaussian. So maybe, okay, here I have computed something about the maximum of the square. You want to have something about simply the maximum of xj. For example, you can just use Jensen inequality. So if you use Jensen inequality, what you have is that the expectation of the maximum is smaller than the square root of the expectation of the square of the maximum. Now you know that the square of the maximum is always smaller than the maximum of the square, so you can use it here. And you can plug the bound that we have obtained in order to get this bound on the expectation of the maximum. So this is the first way to obtain bound. So this inequality is the first way in order to obtain bound on expectation of maximum. But indeed, we can generalize this in order to get better bound. So let us look at this generalization. So I state it as a lemma, even if it is just a 3-line proof, because it is an important inequality. So if you take any function phi, which goes from a real interval to R plus, so you need that phi of x is non-negative, and you want phi to be convex, okay, so you really need phi to be convex, then what you have is that phi of the expectation of the maximum is always smaller than the sum of the expectation of phi. Okay? Why is it true? Just have a look. So we take phi of the expectation of the maximum. As before, we apply Jensen inequality. So this is smaller than the expectation of phi of the maximum. Just as before, we use the phi that phi of the maximum is smaller than the maximum of the phi. Okay, always true. And now this is non-negative by assumption of phi. So I know that the expectation of the maximum of phi is smaller than the sum of the expectation. Okay, so you always have this bound for any function phi which is positive, so non-negative and convex. So let us have a try to use this inequality in order to get a bound on this expectation here. So what I will do is to use as a function phi exponential s of x. Okay, so I am in the case where I have Sub-gaussian random variables. So I know something about the expectation of exponential s of xj, so this sounds good. So let's have a try. So if I take this lemma, I know that, so I will inverse phi. I know that expectation of the maximum of xj is smaller than phi minus 1 of the expectation of the maximum of the phi. Okay, and this maximum is smaller than the sum, so I should have said the sum because it was the sum that I had directly in my lemma. So what I obtain that it is smaller than 1 over s, the logarithm of the sum of the expectation of s of xj. Right? So now, what can I say about the expectation of xj? So I have Sub-gaussian random variables. And for Sub-gaussian random variable, this is smaller than exponential sigma 2 s2 over 2. So I can plug this value. What I do here. And if I plug this value, so what I have is logarithm of p times this exponential. So this is log p plus log of the expectation of the exponential. So this is just log p plus s2 sigma 2 over 2. And all this is divided by s, so I have log p over s plus sigma 2 over 2 times s. Okay, so this bound is true for any value of s. And again, what I want to do is to do some optimization in s, so I will choose s equal to square root 2 log p over sigma square. And for this choice of s, what I've obtained is that this maximum, the expectation of this maximum, is upper bounded by sigma square root of 2 log p. Okay? So this is a very important result. So This is true for Gaussian variables, and actually it is true for any sub-Gaussian random variables. If you take the maximum of p random sub-Gaussian random variables, the expectation is smaller than sigma square root 2 log. Okay, and if in addition you will use Gaussian concentration inequalities, so if you are in the Gaussian case, then you will have that the maximum is smaller than this quantity plus deviation, which will be at most sigma square root of 2 times an exponential random variable. Okay, so this is a very powerful tool in order to have some control on maximum of random variables. Okay, so all what we have seen here works where we replace a maximum by a sum. Okay, so this will work for a finite number of random variables, but what if we have an infinite number of random variables? Okay, let me give an example where we want to control an infinite number of random variables. For example, assume that I have a matrix X, which is n by p, okay? And assume that all the entries of this matrix are IID with standard Gaussian distribution. And what I want to control is the operator norm of X. Okay, so I want to know something about this. And what is the operator norm of X? Okay, we know this is the maximum over all the u in the unit ball of the norm of XU. All right. So if I use bound like this one, I will end up with the sum over all the u in the ball of some expectation. And of course, you have the sum over an uncountable number of quantities. So this is plus infinity, unless this should be 0, but it is not 0. So this is plus infinity. Okay, so this is true, of course, that the operator norm of X is smaller than plus infinity. But I don't believe that you will do any interesting analysis with this. So you need to do something smarter. So do you have an idea, okay, about what you could do to handle this case? So the idea is the following. So you will not be able to apply the previous scheme to all the points in the unit ball because there is an uncountable number of points, but you can maybe try to approximate your maximum over all the ball by a maximum over a finite set n epsilon. And as a set n epsilon, what we will take is what we call an epsilon net. So what is an epsilon net? It is just a net of the ball such that any point in the ball is at distance at most epsilon of the point of the epsilon net. Okay? So why is it a good idea? The idea is that instead of taking all the maximum over all this ball, so we take all the maximum about these blue points here, and if you look at the maximum here, so this is this maximum plus the difference between the maximum on the ball and the maximum on the net. And the idea is that if you look at the norm of XU, this is something which is continuous with respect to U. So the maximum between all the points of the maximum over the point on the epsilon net should not be that different. And this is indeed something that you can check. If you look at the difference between XU and XU prime, where U is in the ball and U prime is the epsilon net, is in the epsilon net and at distance at most epsilon, you see that this is always smaller than the maximum over the point which have a norm at most epsilon of XU. All right? And this, you know that it is smaller than the operator norm of X plus times epsilon. So what it means is that for epsilon small enough, this quantity will not be too large. It will be at most the norm of the operator norm of X times epsilon. Right? And for this term, you can handle it exactly as before by applying this kind of inequalities. All right? So this is a way in order to get bound on expectation of a maximum over the unit ball of the XU by decomposing on a finite set on a remaining term. So this is not something that we will do together. This is something that you will see with Mathieu Leral, but it was just a glimpse so that you can see that we can go beyond a finite number of random variables. And also, so this is sometimes it is quite crude. It is not enough to do this kind of decomposition. And what you have to do is decomposition at different levels. So you have different epsilon net for different value of epsilon, donc some kind of zoom in. And this is what we call a chaining argument. And again, Mathieu Leral will explain all of this to you during his lecture. That's all for today. So see you next week for a new lecture on model selection on